Okay, so we're going to be doing something a little bit different today. I have a couple friends who are in TSM 477 with me, and they're at APME conference. So they missed this class, so we're going to be explaining to them a couple different kinds of problems that we did on class, and we'll see how it goes. I don't have as good a stories as Nir, so stick with me. So today we're going to be looking at the first problem is a missile launching system. This was actually implemented on the Apache attack helicopters, and they're having issues with them. So we're going to look at their logic gates and figure out where they went wrong. So the three conditions to fire a missile were this missile sight was locked on target, the safe release switch was depressed, and the firing trigger is then pressed, and that's how it was supposed to work. This is a diagram of those logic controls, and you're given this in the problem. I just drew it out so it's a little bit bigger. On the far right here, we have our operators. So the top one is OR, so that's a union. The middle one is AND, so that's an intersection. And this third one here is a NOT. So anytime that you have this in the equation, it's what that isn't. So looking at our diagram, we solve this. It looks pretty complex, but if you solve it piece by piece, it's actually pretty easy. These outside little circles where we have 3/4 of a rectangle that goes around it means that that's not in the input. Whenever you have a straight cross, that means it does have an input. So we have one cross and three of those that they're not included in the input. It's actually 2 crosses. I apologize, I can't count. So now that we have the parameters of the equation laid out, we're going to start solving it. So I always find it's easiest to start out as your easiest solution and then work from there until you get to the most complex part, because most of the time you're going to have most of the problem solved before you get to really complex areas. So we're going to start out with our input at A. We're going to solve this top tree first, and then we'll solve the second tree. So the top tree, you can see we have an input here at the NOT. So what we're going to do is we're going to put an A NOT right there. And then you can see we have an intersection here of B and C with that. So now we connect those three together, but we have to have an operator with it. So it's saying that all 3 inputs are coming into this, and that is an AND. So that is an intersection. So here we have A NOT intersection B intersection C. So that's that top tree. So we solved the easiest part, and then we just kept adding to it. Now we go to the more complex tree. 3, this one is not included. As you can see, it goes around it, so it's not an actual input of this. B goes around it as well, also not an input, and so does C. So we just have straight here, and it's the same exact thing, except no NOT on the A. Very important. So now we have this part solved and this part solved, but we have another operator here. And this operator is the OR, which is union. So, and then this is D. It almost looks like another operator, but it's not. This is our final output. So we add these two together, we get A NOT intersection B intersection C union A B, intersection C. So that's what our final output looks like. So there's one more part to this problem. D equals 2. So we have to have this condition 2 met in order for this system to work, and then we can go over and answer these 3 questions. So A NOT intersection B intersection C. So we can replace these with multiplication symbols and the union with an addition symbol. So here's your union, and that's plus. We have A times B times C. So we can see that when we fill it in, it begins to look less and less complicated. So 0 is a NOT, and 1 is your regular. So we have 0 times 1 times 1 plus 1 times 1 times 1. So using your order of operations, this side equals 0, and this side equals 1. So 0 plus 1 equals 1. So we have d equaling 2. And in this system, d does not ever equal 2. So this is not true. D will equal 1. So we go over, we say, will the system fire at all intended conditions? The answer is no. It will not fire at that. No. Are all systems functional? The answer to that is also no. And what it is it's that A naught. So that A naught is the sights are locked on target. So this is very important because what this is saying is that you can fire a missile without having a lock on it, which may not seem like that big a deal, and except the way that these guys were being trained is that they would depress the firing trigger and the safety before they would have the sight locked on target, simply because if you depress the trigger and the safety, and you want that missile to be going as soon as possible. So, bad idea if that's how you're going to train your people. If you're saying that your sight has to be locked on target before you depress the trigger or after depressing the trigger, and they were obviously trained to fire first and let the computer do the work. So that's the condition that it has happened, and they actually did have a couple of these that released prematurely because the system said it had a green to go and the sight locked on target was not part of the equation. So fault tree versus event tree. So we have done event tree in the past, we have not done a fault tree. So a fault tree, the difference between the two of them, we start with our desired events and we weigh all options. We also know what is going to happen here. With the event tree, we're a little bit more unsure of it, and we're looking at a beginning event to an end event versus we know what's going to happen, and we're starting from the bottom here and going backwards. So a very easy way to do this is looking at gambling. So we're all really good at gambling. That's why we came to Iowa State. And we look at a top event, which is rolling 7. With 2 6-sided die. So this is our output that we want, and then we're going to say, how do we get there? So we can roll a 1 and a 6. And dice 1. And dice 2. So this one's going to be 1, and this one's going to be 6. So we have A and B, and we have another one here. Also, once you get to something that you know the probability of, it stops. So we have 2 events here, we split them out, but we know the probability is both of these. Now, the same 2 dice, and in converse of that, we roll a 6 and a 1. So this is dice A getting a 6, and dice B getting a 1. We just keep building this out. Don't worry, I'm going to speed this up so you guys don't have to watch me draw all this. But I think it's very important to see that the beginnings of this, we'll do 3 events and then I'll speed it up. So now we have a 2 and a 5. So dice A gets 2, dice B gets 5. So you can see I got a little overzealous and drew my line a little long, but we have 6 events that meet this condition of 7. And since any one of these 6 events, this is where the new material comes in, any one of these 7 comes in play, we can have an OR here. So this is OR. And then this is an AND here at this gate. So both of these conditions must be met. So it's 4 and 3. That's where we get that and that's why I drew that in there. And, actually, or, but the top event, which we're really focused on, it's just any one of these 6. So what we have is a combination of A and B. So A intersection B of these 6 events, which we would write as 6 and 1. And we can continue this out, plus, so this is where that goes into that union. This would be union here. Basically, we draw this whole thing out. Now, I'm pretty sure all of us know what dice are, but the possibility for each one of these is probability, excuse me, is 1/36, because you have 6 outcomes here and 6 outcomes here. So each one is 1/36, but you have 6 events that are acceptable. So you have 1/36 plus 1/36, and you have this 6 times, which, ooh, that ellipsis was not very good, which turns into 1/6. So the probability of this occurring, rolling a 7, is 1/6. Pretty straightforward stuff. That's a very basic example. We're going to go with one more example here quickly, and that should give you a better idea of how we can use this in real life situations. So the final problem that we talked about in class was the space shuttle failure. So we identified a couple different ways that it could fail. So the first one, this was an actual event that happened. We talked about it earlier in class, was thermal protection failure, where they had a piece rip off and then they had to stick it back together. Mechanical integrity of the structure of the shuttle fails. We've had that a couple times. Human error, we've also had this a couple times that we've seen in launches. And then steering system failure. Now the one that we explored in class was the steering system failure, simply because it's the easiest to calculate out of all of these. So we have a steering system failure, and what we have here is we have 2 systems that run by each other. So we have our main system, and then we have emergency system. We'll abbreviate that. So the main system is run by 2 systems side by side, or excuse me, 2 loops side by side, and both of those need to be functioning in order for the actual system to work. So breaking this down a little bit, it's a very simple problem, but what you have to realize is we could build this out on each one of these trees 5, 6 levels down, and we're not going to do that right now for time's sake. But just realize that each one of these could have a number of different events that come off of it. So you have several different kinds of thermal protection on the shuttle. So that would be several different events, and then each one of those would have a probability associated with it. And we only go until we have a probability of failure. So we know the probability of failure of each one of these systems. So that's where we'd stop there. So this is system 1 and system 2. So calculate that out simply, and turning it into a Boolean algebra-esque problem. So 1 and 2 must be functioning for it not to be a failure. So what that would be is at here, and would be this operator, so an AND operator, and then we build it back up, which any one of these systems would be a failure. So we have an OR, so a union of it, because we're looking at the system space shuttle failure as a whole. So any failure is a failure nonetheless. So it doesn't matter if it burns up, it doesn't matter if it rips apart, it doesn't matter if we re-enter the atmosphere at too tight of an angle, because we thought that we were going, too direct into it, or if we can't steer it. Any one of those are deemed as a failure. And then that changes, but the operators change when you actually get inside the systems. So this is a very simple problem that we look at, but we have to realize that when we actually do this, it can become very, very complicated very, very quickly. So that's the third kind of problem that we did. No. Oh, yeah, that is the third kind of problem that we did. Hopefully that helped a little bit. Thank you guys for representing us at APME. We really appreciate it, and hopefully you guys had a good time too.